Welcome viewers. Today we will be discussing quadratic forms. This lecture includes quadratic forms and positive definite quadratic forms. The prerequisite to this lecture is eigenvalues and eigenvectors together with diagonalization. I suggest that before going through this lecture, the user must go through the eigenvalues and eigenvectors together with diagonalization. We start with quadratic forms. We all are familiar with this quadratic form ax square plus 2bxy plus cy square is equal to d. We call it a quadratic form because this has x square term, xy term and y square terms in this expression, and all these terms are quadratic. So, we say this form is a quadratic form provided a, b, c and d are real numbers, and for these real numbers this expression represents a conic section in two-dimensional plane. We call it a conic section because it is obtained by cutting cones by planes. These forms are used in many applications, and that is why we are discussing them in this lecture. This is a particular form. The more general form may be ax square plus 2bxy plus cy square plus linear terms dx plus ey plus f equal to 0. This is more general form than this. It has all the terms which are quadratic, but this may have linear terms also. Now, general form is very difficult to recognize, so we consider the forms as a standard form in which we do not have any cross product terms and linear terms like xy, x square or y square and ax and terms like dx plus ey etc. So, a term an expression which is free of these linear terms as well as product terms is called a standard form. Its center is origin of rectangular coordinate system, that is why this is preferred. Like we have x square plus y square is equal to 1, we know it is a circle, does not have any cross terms here, does not have any linear terms. So, it is a standard form of a circle having center at origin and radius 1. Similarly, we have x square by a square plus y square by b square is equal to 1 represents an ellipse. Again, this is free of cross terms and linear terms. Another form may be x square over a square minus y square over b square is equal to 1, it represents hyperbola. And we may have a form y square is equal to 4ax or x square is equal to 4ay, it represents parabola. This is a circle, we all are aware of this. Now, this represents an ellipse. The here these are equal, but in case of ellipse the major axis and minor axis, these components are different. Now, this represents a hyperbola, the yellow lines, yellow curves, these are the axes and in fact these are the asymptotes of the hyperbola. In case of parabola, this is a parabola, or parabola may be like this. Now, if cross product terms are present, then we can bring again into a standard form by suitably rotating the axis. So, if cross terms are present, then rotation of axis is required and we may get an expression which is in standard form. For example, xy is equal to 1 is this curve. So, we have rectangular axis and these are the curves representing xy is equal to 1. But if you rotate this axis, then the curve will look like as this, and this xy is equal to 1 will transform to y square minus x square is equal to 1 by suitable transformation, and here we do not have any cross term present over here, but this curve is the same as this, only thing is you have to rotate this axis. So after rotation, this was the previous axis before rotation, and when you rotate it, it will be the new axis. So this curve and this curve, they are same, only difference is that this curve is rotated. So after rotation, cross terms can be eliminated and one can very easily recognize this to be a hyperbola. Similarly, this represents an ellipse ax square plus bxy plus cy square is equal to 1 for suitable values of a, b and c, and then after rotation of axis, this axis, then we will have this ellipse and the equation will be transformed to 2x square plus y square is equal to 1. Now this is the original axis and after rotation this is the new axis. So on the new axis it is 2x square plus y square is equal to 1, which is standard form, and no cross terms are present over here. Now what is the effect of translation? Translation is required when linear terms are present to bring the system, to bring the given quadratic form into standard form. For example, if we have been given this ellipse and the expression for this will require linear terms also, but if you translate this axis, that means you shift this origin to this place, then it will be a normal form. So you are shifting this origin to the center of the ellipse and this will now be in a standard form. So whenever linear terms are present, one has to shift, one has to perform translation to get the normal, to get the standard form of the quadratic. Now the identification of conic section requires rotation and translation of coordinate axis so that we can easily recognize by its standard form. So this rotation and translation is required to bring the given quadratic into the standard form, and from there one can easily recognize the quadratic. Now these methods can be better appreciated with matrices and their eigenvalues and eigenvectors. See, what I have tried to explain here is the case of 2 dimensions, but if we are having 3 or more dimensional quadratic forms, then things will be difficult to visualize, but with the help of matrices and eigenvalues and eigenvectors, one can very easily identify the quadratic forms. So in general, let us say we have a 3-dimensional surface, we call it a quadratic surface, which is ax square plus 2bxy plus 2cxz plus cy square plus 2fyz plus cz square is equal to g. So this is a quadratic form in 3 dimensions for a, b, c, d, e, f, all the coefficients being real. Now if not centered at origin, the form of equation will be more complex. Now there are no linear terms present in this, so it is centered at the origin, but if these terms are also there, then the surface will not be centered at the origin and form will be more difficult. In general form, the quadratic is written as x transpose ax plus bx is equal to k. This is a matrix equation where A is a square matrix and x is a column vector. Now we come to the quadratic forms. Some examples. If we consider this quadratic form 2x square plus 3xy plus y square in 2 variables, then we can write this quadratic form in the matrix form as x transpose Ax, where x is a column vector x and y. How we get the matrix A? A is a square matrix of order 2 by 2. So we write this 2 and this 1 in the diagonals, and this quadratic cross term is written as 3 here and 0 here, and that makes the matrix A as 2 3 0 1, and let us see that this actually represents this quadratic. So let us multiply this. So we have 2x, and this multiplied by this gives me 3x plus y. When multiplied by xy, this gives me 2x square plus 3xy plus y square. So this given quadratic is equivalent to this matrix representation, where A is this 2 by 2 matrix. But this representation is not unique. You can check that we can write down the same quadratic in this form, like we have A as 2, 2, 1 and 1. What we have done is that we have broken down that 3, the cross term, in 2 parts. So 2 is here and 1 is here, and accordingly when we multiply, it is 2x plus y, and this multiplied by this is 2x plus y multiplied by this column vector will give the same expression, 2x square plus yx plus 2xy plus y square equal to 2x square plus 3yx plus y square. So if we break down this term as 2 and 1, we will be getting this. You can break it as 1 and 2, again one can check that we will be getting the same expression for the quadratic, and this is not unique. You can break down in any number of ways and you can have corresponding matrix A. So this qxy can be written in many different ways as x transpose Ax, and A may have different values. However, there is only one way in which the matrix A is symmetric matrix. So if we want to write down a matrix which is symmetric, then we can have only one possible way to represent this quadratic as this matrix. So let us see how we do this. For symmetric matrix, we divide the product term into 2 equal parts. That is, if we have this quadratic, then 3xy is divided into 2 parts, 3xy by 2 here and 3xy by 2 here, and that makes the matrix A as 2 and 1. 2 is this square term, this 1 is this square term, and 3 by 2 corresponding to this and 3 by 2 corresponding to this. So this matrix is the associated matrix A with this given quadratic, and one may notice that this is a symmetric matrix. In the next example, I am considering a 3-dimensional surface, 2x square plus 3xy plus y square plus 2xz plus yz plus z square. So I need qxyz is equal to xyz and a 3-dimensional 3 by 3 square matrix A multiplied by the column matrix xyz. So this 3 by 3 matrix is obtained as first term 2 corresponding to this term, then corresponding to this I have 1 here, from here I will be having 1 here. This 3xy is divided into 2 equal parts, so 3 by 2 here and 3 by 2 here, only x and y part, but 2xz will contribute here and here. Since it is 2, so half of it 1 is here and half of this is appearing here, and yz will appear in this part. It is yz, so half of yz is coming here and another half is here. So that is how I obtain this matrix A. In general, if I have a quadratic expression in n variables, then this can be written in this form: summation bij xi xj, I and j varies from 1 to n. So how to get bij's? So I write bij as bij plus bji by 2 multiplied by xi xj. So I am writing this expression in this form, and from here I can get the matrix aij. So aij is a typical element of the matrix A, and this is equal to bii when I is equal to j, and when I is not equal to j, that means corresponding to cross terms, I will write down this as bij plus bji by 2, and if this is what I am doing here, so bij and bji is 3 here, so divided by 2, that is aij, and if I define my matrix Aij in this manner, then one can easily observe that Aij is equal to Aji, because if I is equal to j, they are equal, and when I and j are not equal, then Aij is equal to Aji. So, for the matrix A, I have Aij is equal to Aji, and that simply means that the matrix is symmetric. So, with this definition, I can always represent a given quadratic in the matrix form where the matrix is a symmetric matrix. Now, I formally define quadratic form. We say that if A is symmetric matrix, then the real valued function g from Rn to R1 defined as Gx is equal to x transpose Ax, where x is a column vector x1, x2, xn transpose. It is called a real quadratic form in the variables x1, x2, xn. So, if we can define such a function Gx represented as x transpose Ax, then this Gx is a quadratic form in variables x1, x2, xn. The matrix A is a matrix of quadratic form. For example, if I have a two-dimensional vector x, so we have xy is a column vector, A is a symmetric matrix, A, B in the diagonals and C, C in the non-diagonal terms, then x transpose Ax defines a quadratic form, one can check it easily. In the second example, I have a three-dimensional column vector x and A is this symmetric form, D and D here, C and C here, F and F here. So, it is a quadratic form. By suitably changing the variable x is equal to py, where p is a non-singular matrix, we can write down the quadratic expression px, x is a column vector, is equal to py transpose, that is what I am writing for x transpose, A multiplied by py. One can simplify it, it is y transpose p transpose. So, p transpose into A and p multiplied by y, because multiplication is associative. So, you can regroup the terms, and what we have is y transpose by. Now, we can say this qx is now transformed to another quadratic in y, we call it q1y, it is y transpose by. So, a quadratic can be transformed to another system, and this transformation will be x is equal to py. So, we have given initially qx and then we have transformed it into q1y. Now, we define that if A and B are square matrices of order n, then B is congruent to A provided B is equal to P transpose AP for a given non-singular matrix P. So, the two matrices A and B are congruent if they are related by this expression. So, B is equal to P transpose AP for some non-singular matrix P, then B and A are congruent. And we can also say that A is congruent to B if this condition is satisfied, and maybe we can in short say that A and B are congruent. In fact, congruence is more general concept than similarity of symmetric matrices by an orthogonal matrix P. Since we have already gone through this lecture on similar matrices, we say that B is equal to P inverse AP, then B is similar to A, and when P happens to be an orthogonal matrix, then P inverse and P transpose, they are same, and in that case we can say that this is nothing but B is similar to A, where P happens to be an orthogonal matrix. But congruence is a more generalized concept than simply symmetric matrix, or it's more general concept than similarity of symmetric matrices by an orthogonal matrix P. Hence, here for this concept we require P has to be a non-singular, which is not the case in this relationship. We further prove that congruence is an equivalence relation. By equivalence relation I mean to say that A is congruent to A, and if A is congruent to B, then B is also congruent to A, that is symmetric relation. And finally transitive, that is if A is congruent to B and B is congruent to C, then A is congruent to C. So, in these things can be very easily proved, and we conclude that congruence is a equivalence relation. The quadratic forms Qx and Q1y are equivalent if the matrices A and B are congruent. So, this is what we derive. Let us check. In the example, if Qx is 2x square plus 2xy plus 2y square, then Qx can be written as x transpose Ax, where A is the corresponding matrix. It is 2, 2, and this term is 1 and 1. So, this is the representation for Qx. Let us write down changed system uv is equal to p times the original system xy, where the matrix P is, let us take this matrix P is 1 by root 2, 1, 1, minus 1, 1. How we arrive at this matrix, that I am not discussing at the moment, but if we use this transformation, then Q1 comes out to be uv P transpose AP multiplied by uv, and that means if you perform this multiplication, then Q1 comes out to be, we have substituted these values here, Q1 comes out to be u square plus 3v square. The idea is I have started with this quadratic in which some cross terms are present, but after this transformation which I have applied here, the final form, the congruent form is free of cross product term. So, it is now written as u square plus 3v square. That means, given a quadratic, we can transform into a form where cross term will not be present, and we know that handling such things are simpler as compared to this. So, Qx can be transformed to a more suitable equivalent form as u square plus 3v square. It is free of product term, and this can be done for, this is an example only, this can be done in general, and for that we will have principal axis theorem. According to this, the quadratic form Qx is equal to x transpose Ax is equivalent to this form Q1y is equal to y transpose By, which is lambda 1 y1 square plus lambda 2 y2 square plus lambda n yn square, where lambda 1 happens to be the eigenvalues of the matrix associated with this quadratic A. So, B is a diagonal matrix and these terms are the eigenvalues of the matrix A. So, this is called principal axis theorem. So, for a symmetric matrix this is possible. So, let us try to prove this. Here is the proof. We consider Qx as a quadratic represented as x transpose Ax. A is the associated matrix and it is a real symmetric matrix. Now, A can be diagonalized by an orthogonal matrix P such that D is equal to P inverse AP. This is the result which we have already discussed in my earlier lectures. So, if A is a real symmetric matrix, then it can always be diagonalized by an orthogonal matrix P, which is the matrix of eigenvectors of this matrix A. So, if P is a matrix of eigenvectors, then P inverse is P is invertible. So, P inverse exists, and in that case G is equal to P inverse AP will be a diagonal matrix. And since it is this P inverse I can write it as P transpose because it's an orthogonal matrix. So P inverse is equal to P transpose. So D will be P transpose AP, or we can say, if we can write down D in this form, then by the definition of congruent we can say that A and D matrices are congruent. Now this is possible because P is orthogonal, that is all I have already explained, and the diagonals of D are eigenvalues of A. So all this requires the earlier lectures on diagonalization. And with this Qx is represented as X transpose Ax equal to X transpose P transpose AP X, and then we can use this substitution y is equal to Px, and then we can easily check that Qx will transform to Q1y. So Qx is written as Py transpose APy. This simplifies to y transpose P transpose A Py. We can regroup the terms, and it is y transpose multiplied by P transpose AP multiplied by y, and I write down P transpose AP as B. So this expression becomes y transpose By. So this Qx is now transformed to Q1y, where B, this is again a quadratic form, but the associated matrix is B. So A and B are congruent matrices. So the forms Qx and Q1x are equivalent, and application of orthogonal diagonalization does not require the matrix P, or eigenvectors need not be computed, only eigenvalues of A are required. So that is the advantage of this form. You do not have to require the matrix P, only the eigenvalues are required. This is illustrated in the example. So let us consider the quadratic form 4 multiplied by x1 x2 plus x2 x3 plus x1 x3 is a quadratic in 3 dimensions. So determine its equivalent quadratic form Q1 xyz, which is in which the associated matrix is a diagonal matrix, or this form is free of cross terms. So let us consider the matrix corresponding to this. Since all the diagonal term, all the square terms are absent, so diagonal will be 0, and it is 4 times, so it is 2 here and 2 here corresponding to x1 x2, and this 2 and 2 corresponding to x1 x3, and this 2 and this 2 corresponding to 4 times x2 x3. So this is the associated matrix with this quadratic form. Now to find eigenvalues, consider this characteristic equation. It is determinant of lambda I minus A. So this is lambdas minus lambda will appear in the diagonal, and this is rest of it is A. So it is A minus lambda I equal to 0, and you simplify it, the characteristic equation will come out to be, this is a simplification, and this gives me this expression, which will be further simplified to give lambda is equal to minus 2 and minus 2, and one eigenvalue is 4. So 2 roots are repeated and 1 is 4. We have 3 eigenvalues for this given matrix A. So the equivalent quadratic form is simply minus 2y1 square minus 2y2 square plus 4y3 square. We do not have to calculate, we do not have to compute P and P transpose and perform the multiplication to arrive at this quadratic form, only eigenvalues are needed. So there are 2 eigenvalues, minus 2 minus 2, so we have 2 terms, minus 2y1 square minus 2y2 square corresponding to them, and third term is 4 because the eigenvalue is 4. So we have here 4y3 square. Another equivalent form may be this. Here again, here again I am having two eigenvalues -2 and one value 4, but what I am doing here is I am associating these two negative values with y2 and y3, and while 4 is associated with y1. In this case 4 was associated with y3. So, these are alternative forms and they are equivalent. Now, we say this theorem as a principal axis theorem because y1, y2, y3 are actually the principal axis of the quadratic surface, and these axes lie along y1, y2, y3 axis in the new system, and that is the reason we say this form is a standard form, and the theorem changes our coordinate axis to corresponding principal axis, and that is why we say the theorem as principal axis theorem. Now, these are some of the results which we have obtained earlier, and actually these forms the basis for finding out Q1y. We know that eigenvalues of symmetric matrices are real, so these values are real. So, we can always transform our given quadratic in this form where all these coefficients are real, because eigenvalues are real. So, this is always possible. If eigenvalues of a matrix are complex, then this would not have been possible, but since the matrix is a symmetric matrix, so the eigenvalues are always real, and we can always find out this form. And existence of Q1y is guaranteed due to the real eigenvalues. So, if lambda 1, lambda 2, lambda n are the eigenvalues of A, then the Qx, which is given as x transpose Ax, can be transformed to the real eigenvalues lambda 1, lambda 2, lambda n are arranged in a manner so that all positive eigenvalues appear first, and then all negative values, and finally the zeros eigenvalues. So, if lambda 1, lambda 2, lambda p are real positive values, and lambda 1, lambda 2, lambda r are real values, then lambda p plus 1, lambda p plus 2, lambda n are 0 values. So, R happens to be the rank of the matrix P, and out of these R, P are positive and remaining will be negative, while lambda p plus 1 to lambda n all eigenvalues are 0. Now, we consider another diagonal matrix H with diagonal elements as 1 over lambda 1, 1 over lambda p, 1 over under root lambda p plus 1, and then the negative terms are written with minus sign under root. So, lambda r is negative, so we write it as minus lambda r, it is under root, and then we write down 1, 1, 1 corresponding to these 0 values. So, I form a matrix H with these eigenvalues. Now, let us consider this matrix D1 as H transpose DH. Now, H, D and H are all diagonal matrices, and H is having positive terms as 1 over under root lambda, and H transpose is also having 1 over under root lambda, while D is having under root lambda. So, when you multiply this, every term in the diagonal of D1 will be either having 1 or will be having minus 1, depending whether the corresponding eigenvalue is positive or negative, and then the values corresponding to 0 will be having 0 over here. So, D1 will either be having 1 or minus 1 or 0. So, this way we can write down the diagonal matrix D1, and once we can express D1 as this matrix, we can say that D and D1 are congruent, and that means a given quadratic Qx is equivalent to a quadratic form Q2y, which is equal to y1 square plus y2 square plus yp square positive terms minus yp plus 1 square minus yp plus 2 square up to yr square with negative terms. The rank of this associated matrix was R, so we will have at the most R terms. Some of them will be positive, some of them will be negative. The difference between Q1y and Q2y is that in the coefficients, in Q1y the coefficients are eigenvalues, but in Q2y the coefficients are +1 or -1 depending upon the sign of corresponding eigenvalue. So, for a given matrix Qx, we can always transform it into a form where Q2y is y1 square plus y2 square plus yp square minus yp plus 1 square up to minus yr square. So, this particular form is called canonical form. So, when P is fixed, Q2 is unique. So, this is the result which we are having, and a given polynomial can always be transformed to the corresponding canonical form, and it is a unique form. Now, I will introduce a term inertia, which is a triad consisting of 3 values. This first value represents how many eigenvalues are positive. The second term represents the number of negative eigenvalues, and 0 is the number of 0 eigenvalues. So, inertia associated with a given quadratic is a triad indicating the number of positive eigenvalues, negative eigenvalues and 0 eigenvalues, and from there one can find out the canonical form. Now, the difference between the number of positive eigenvalues and negative eigenvalues is called the signature of quadratic form. So, if I am having p number of eigenvalues which are positive and r being the rank, then r minus p will be the negative eigenvalues, remaining will be 0. So, p minus r minus p is equal to 2p minus r. So, we say that 2p minus r is the signature of the quadratic form. We say if Q1 and Q2 are equivalent quadratic forms, then they have same rank and same signature. These are easy to prove. This result is easy to prove. Then the next result is that Q1 and Q2 have same rank and signature, then they are equivalent. This is just converse of this. Let us illustrate this with an example. I have been given a quadratic 4y1 square minus 2y2 square minus 2y3 square. Its eigenvalues are 4 minus 2 minus 2 and d is 4 minus 2 minus 2. Actually, this quadratic is being taken from earlier example, and we have already computed the eigenvalues of that matrix as minus 2 and minus 2. So, for this quadratic, eigenvalues are 4 minus 2 minus 2, and correspondingly we have the diagonal matrix as 4 minus 2 minus 2, and off diagonal terms are all zeros. Then the eigenvalues of h will be 1 by 2. It is under root of 1 by lambda. So, it is 1 by 2, and then the next eigenvalue will be 1 by minus of the eigenvalue. So, that is why it is coming out to be 1 by root 2, and another eigenvalue of h will be 1 by root 2. Now, let us now compute d1 as h transpose gh. So, I am writing h transpose. Now, h is a diagonal matrix, so its transpose will be the same as h, and values in the diagonal will be 1 by 2, which is under root of 1 by 4, then 1 over under root 2, it is under root of minus 2. So, it is 1 by root 2, and we have 1 by root 2. Then this the matrix D. Diagonal elements I have not shown here, but they are 0 elements, and we will have this diagonal matrix H. When you multiply it, this multiplied by this and this multiplied by this is 1, this and this multiplication gives me minus 1, this and this is minus 1, and correspondingly we have D1 is equal to a diagonal matrix with 1, minus 1 and minus 1. Accordingly, Q2y comes out to be y1 square minus y2 square minus y3 square. So these are two negative eigenvalues. So it is minus y2 square minus y3 square, and since it has one positive eigenvalue and two negative eigenvalues, so we can say P is equal to 1. Rank of this matrix is 3. So number of negative values will be R minus P, that is 2, and from here inertia is positive values 1, negative values 2, 0 values is 0. So number of 0 values is 0 here. So inertia is this triad, and signature of this quadratic form is S is equal to minus 1, because we are having more eigenvalues compared to more negative eigenvalues compared to positive eigenvalues. So signature comes out to be negative. Now we start with the general form of the quadratic equation, x transpose Ax plus Bx plus D equal to 0. Of course, we have till now concentrated on this part, x transpose Ax. So let us consider we have a general form, x transpose Ax plus Bx plus D equal to 0. Then if A is not diagonal matrix, then we rotate it by this transformation, x is equal to Py, and it will become diagonal matrix. And if B is not 0, then we translate the axis so that we can get rid of this, and we finally have x transpose B x, or we can say y transpose B y plus D equal to 0. So this can be easily converted into a standard form, and the classification of this standard form actually depends upon this eigenvalue problem, Ax is equal to lambda x, and that is how we identify or classify 2D surfaces. See, this eigenvalue problem, if it has two eigenvalues which are positive, then the corresponding standard form will be an ellipse. Its inertia will be 2, because number of eigenvalues are 2, it is 2 dimensions, so negative values will be 0 and no eigenvalue is 0 in this case. It is hyperbola when both the eigenvalues are negative, when the product lambda 1 and lambda 2 is negative. So one eigenvalue is positive and one eigenvalue is negative in this case. So 1 for number of positive values, 1 negative eigenvalues, no value which is 0, and it is parabola when one eigenvalue is 0. So either lambda 1 is equal to 0 or lambda 2 is equal to 0, then it will represent a parabola. It has one positive value, it has no negative value and one 0 value. So depending upon the inertia corresponding to given matrix, in the given representation, we can classify the quadratic as ellipse, hyperbola or parabola, and corresponding inertia is given as this. Now for 3D surfaces, we can similarly classify quadratic surfaces. We say if inertia is 3, 0, 0, then it is ellipsoid. That means all the 3 eigenvalues are positive, no eigenvalue is 0 and nothing is 0. No eigenvalue is 0 in this case, then we have ellipsoid. And when inertia is 2, 0, 1, then we call it elliptic paraboloid. So 2 eigenvalues are positive, one value is 0, no eigenvalue is negative, we will have elliptic paraboloid. When inertia is 2, 1, 0, that means 2 positive eigenvalues, 1 negative eigenvalue, then we say it is hyperboloid of one sheet. When 1, 2, 0 is the inertia, we have 1 positive value, 2 negative eigenvalues, then we will have hyperboloid of 2 sheets. And when inertia is 1, 1, 1, that means we will have 1 positive, 1 negative and 1 0 eigenvalue, then we call that surface as hyperbolic paraboloid. 1, 1, 2 represents a parabolic cylinder. So that is how we classify different surfaces. Now in this example, you have to identify the conic section. So the conic section is given as x square plus y square plus z square minus 4xy is equal to 4. It's a 3-dimensional surface. So to identify what it represents, we have to calculate its inertia. For that, we have to first write down the corresponding matrix A, and terms in the diagonal are 1, 1, 1, and this minus 4 corresponds to minus 2 and minus 2 in this position in the matrix A. Then we calculate the eigenvalues. For this, we consider the characteristic equation as this, and this simplifies to this equation, characteristic equation, lambda minus 1 multiplied by lambda minus 1 square minus 4, and further simplification will give me lambda minus 1 minus 2 and lambda minus 1 plus 2. So the eigenvalues are given from this expression, and they are 1, minus 1 and 3. So we will have two positive eigenvalues, namely 1 and 3, and one negative value minus 1. So the inertia for this given matrix is 2, 1, 0, and according to the classification, this surface is hyperboloid of one sheet. Now we will discuss positive definite quadratic forms. Many times we are interested to know the sign of this expression ax square plus 2bxy plus cy square. It is a quadratic expression. Let us say it is equal to d, and in matrix notation we write it as x transpose ax. So we want to know whether this expression is positive or negative. So we want to know under what conditions this expression is positive, under what condition it may be negative, and under what conditions it is always positive. So those conditions refer to positive definite quadratic form. So I will define the quadratic form is positive definite if x transpose ax is always positive for positive x, and it is 0 only when x is equal to 0. So expression x transpose ax, if it is always positive, then that expression is, or that quadratic form is positive definite. The quadratic form is positive semi-definite when d can be positive for some non-zero x. It may be positive for other values, but there may be some value of x which is not 0, but d is positive. The quadratic form is negative semi-definite when d can be negative for some non-zero x also. So a symmetric matrix A and the quadratic form x transpose Ax are positive definite if x transpose Ax is positive for x not 0. We call the form as negative definite when x transpose Ax is negative for x not 0, and positive semi definite if x transpose Ax may be positive or may be 0 for all x. Negative semi definite when x transpose Ax is negative for all x, negative or 0 for all x, and we say the form is indefinite if we cannot determine the sign of x transpose Ax. If it is positive always, we call it positive definite. If it is negative always, then we call it negative definite for non-zero values of x, and a positive semi-definite or semi-indefinite, a negative semi-definite when we will have these expressions, and if the sign cannot be determined, then it may be indefinite. The quadratic form is indefinite when d can be both positive and negative, can take any value. So in this example we try to decide the positive definiteness of the given quadratic form. So in the first we have the associated matrix as 1 1 1 5, in the second we will have the associated matrix 1 3 3 1, and in the third we will have this matrix. We will go one by one. This matrix is associated with this quadratic expression x square plus 5y square plus 2xy. We can write down this form as x plus y whole square, I am rewriting this expression, plus 4y square. See, x plus y square is equal to x square plus y square plus 2xy. So, 2xy is coming here and y square I have taken from this. So, what remains here is 4y square. Now, this expression is 0 when x is equal to 0 and y is equal to 0, and for all values of x, whether positive or negative, this expression will always be 0, or we can say that this expression is positive definite, or this quadratic form is positive definite quadratic form. It's positive definite. In the second example, I have this matrix, and corresponding to this matrix I have this form x square plus 6xy plus y square, and this form I write it as x plus 3y whole square minus 8y square. And one can notice that for x is equal to minus 2 and y is equal to 1, x is equal to minus 2 and y is equal to 1, then this term will be more than this term, and that makes qx negative. So, this is not positive definite, because its sign will be qx is negative for a value x is equal to minus 2 and y is equal to 1. So, this is not positive definite. In the other example, the 3 by 3 matrix, it is a diagonal matrix. It comes out to be x square plus 2y square minus 3z square. One can notice that if x is equal to 0, y is equal to 0, then if z is whatever be the value of z, then this is negative. So, it is again not positive definite. So, 0 0 1 qx is negative and it is not positive definite. Now, in this theorem we will like to state the conditions under which we can ensure that a given quadratic is always positive definite. So, the theorem states that the following three conditions are equivalent. One condition is if qx is positive definite, second is all the eigenvalues of A are positive, third is all the submatrices have positive determinants. So, I will start with a given quadratic xi transpose AXI is positive. I will first prove that A implies B, means if qx is positive definite, then it implies all the eigenvalues of A are positive. So, with this given positive definite form, let us consider an eigenvalue problem AXI is equal to lambda I xi. Now, in this form A is a symmetric matrix. So, for this form we can multiply this matrix by xi transpose from left as well as on the right. So, xi transpose AXI is equal to lambda xi transpose xi, and we know xi transpose xi is nothing but the norm of xi, which is always positive. So, x transpose AXI is always positive provided lambda I is positive. So, if a given form is quadratic definite, then all the eigenvalues of A should be positive. So, I have started with a positive definite form and I have proved that it has all eigenvalues which are positive. So, A implies B. Now, to consider B implies A, I will start with all positive eigenvalues and I will show that the corresponding matrix is positive definite. So, assuming all lambdas are positive and the matrix A is symmetric, because this matrix is related with the quadratic, then the eigenvalues form set of n independent eigenvectors. This is the result which I am deriving from my earlier lectures on eigenvalues and eigenvectors. So, they form n independent eigenvectors. So, we can write down x, any vector x, as a linear combination of these n independent eigenvectors. So, we will have x is equal to c1 x1 plus c2 x2 plus cn xn. I multiplied by A. So Ax is equal to C1 Ax1 plus C2 Ax2 plus Cn Axn. Then I multiplied by X transpose, pre-multiplication. So it is X transpose Ax is equal to C1 X1 plus C2 X2 plus Cn Xn. This is X transpose. X transpose is X is nothing but this. So this is X transpose multiplied by C1 Ax1 plus C2 X2 plus Cn Axn, whatever I have obtained here. And then if you perform this multiplication, it is column, it is transpose. So if you multiply this, we will have C1 square lambda 1 plus C2 square lambda 2 plus Cn square lambda n square. Since C's are arbitrary, so X transpose Ax is positive, and that means eigenvalues are positive. Because eigenvalues are positive, we will have X transpose Ax is positive, and that means we will have positive definite quadratic form. So we have started with positive eigenvalues, and we could prove that we have a positive definite quadratic form. So B implies C is proved. Now let us try A implies C. So given that Qx is a positive definite, that's the meaning of A. We assume we are having eigenvalues are positive because Qx is positive definite. So B means eigenvalues are positive. So we have this. Then what is determinant of A? Determinant A is product of eigenvectors. Now we consider X transpose Ax as xk 0. What is xk transpose? Is a vector which is having non-zero values and rest of them are zeros. So I reduce this matrix A into K by K matrix, that is AK, and rest of them are these elements in A. So I write it as xk transpose and rest of the elements are 0. So I am considering only those values which are corresponding to AK, they are non-zero, and rest of them are 0. So this particular X transpose is chosen. So accordingly we will have this column vector. So when we perform this multiplication, I will have xk transpose AK X transpose, but X transpose Ax is positive. So xk transpose AK multiplied by xk transpose is positive, provided determinant of AK is positive. This means the submatrix AK has positive determinant. But what is AK? AK is a submatrix of A, and this can be any order matrix. It can be order 1, order 2, order 3, and so on. In fact, this result should be true for all values of K, and that means if we have a positive definite form, then all submatrices will have positive determinant. Now that proves C. That means starting from A we can prove the C. The reverse of this, that is if we have a matrix having all submatrices determinant 0, then we can prove that it is a positive definite form, that is C implies A. I leave this an exercise for the viewer. In this example we are using the theorem which I have just now stated, and with the help of that theorem we like to see whether a given quadratic form is positive definite or not. So if in the first example, if I have a 2 by 2 matrix, then one can notice that its determinant is 1 into 5 minus 1 is positive, and since it has a positive determinant and all submatrices have positive determinant, so it has all positive eigenvalues and it is a positive definite form. So first is positive definite form, but in the second case first submatrix is having determinant positive, but if you consider this submatrix, then its determinant is 1 minus 9 is negative, so it is not positive definite. And in the third case again one of the eigenvalue is negative, so again this is also not positive definite form. So in this example, we will have only one positive definite form. In the second example, determinant is negative, so will not have a positive definite form. In this example, one eigenvalue is negative, then this is also not positive definite form. So only one is positive. Further, if A is positive definite matrix, then A square is also positive definite. I leave this as an exercise for the viewer to prove this. Further, if A inverse is also positive definite, if A is positive definite. So these are two exercises user can try easily. With this we come to the end of the lecture. Today we have covered quadratic surfaces. We have discussed under what conditions a given quadratic form is positive definite quadratic form. That's all. Thank you.
Thank you.